Recording is rolling. It is Thursday, February 6th. So I have some posters lined up. Some of these are going to be a little bit review for fluids, and I got a couple of new things we're going to focus a bit more on. Conservation of flow and Bernoulli principle. So we're going to put fluids into motion and see what happens to like flow rate, speed, pressure, kind of things. Okay. Okay. So there's going to be about probably 15 minutes at the end of class today. I'll give you guys time to work on these puzzles I just handed you guys. So some of these are chapter 13 puzzles. And then if you flip it over, there's some additional puzzles here. And my plan for tomorrow is to give you guys all day class tomorrow to also work on these. Now you guys can work in teams, help each other out. You guys know I make like 100 different versions of these. So there's plenty of different versions, but they're all sort of the same type of questions, just different numbers. Okay. Oh, and I did give you guys your rotational dynamics quizzes back to your folders, and they have scented stickers. Oh yeah, that's fun. You guys remember yesterday, I gave you guys these square of aluminum that was 12 centimeters by 12 centimeters and tanks of water. And I had you guys fold these into little box boats. You guys remember that? Right. It was something to do with this Archimedes principle. We'll tell you the magnitude of a buoyant force is equal to the weight of the displaced water. So when you guys were putting these weights into your boat boxes, they would sink down to the water, but they'd be held up by that buoyant force equal to the amount of, well, I should say the equal to the weight of the water that's being displaced. Okay. Now, see if you guys got this. Right. When you fold up the sides a little bit, you got a little flat box. It probably couldn't hold very much weight at all. Okay. You kept folding and folding, folding. Right. Then it could hold more and more and more weight. But at some point, you fold up the sides too much, and then it can hold less weight. Ooh. So there was an optimal size of a box to hold the maximum cargo. Okay. And what did you guys get? You guys saw that yesterday? What should you fold up each side? I think it should have been two, is what it came out to, right? 2 centimeters. So if you have 12 centimeters by 12 centimeters and you fold up all the way around the perimeter, 2 centimeters, that would give you dimensions of 8 by 8 by 2, right? Because 8 by 8 and then 2 here, too, right? So 8 by 8 by 2, right? That would maximize the volume of the box. Right? If you didn't fold up that much, it would give you less volume. If you folded more than that, that would also be less volume, right? Right. So, all right. So there's a little recap from yesterday. Right, Archimedes principle, buoyant force is equal to the weight of the displaced fluid. Right, you guys remember this whole experiment? Okay, so that's a little bit of review right there. Ooh, guys, look at this row right here. Here, see if you guys follow this. Guys, this row represents what property? Density. Density. Just this little row right here, just this row. Right, guys, this is the density of what? The density of the object or the density of the fluid? Fluid. And what's the density of water equal to? 1,000 kilogram per cubic meter. Right? He also could have said 1 gram per cubic centimeter, but what I'm trying to get is this is an intrinsic property to some material. So water is always, let's call it 1,000 kilograms per cubic meter. Iron has some density, aluminum has some density. Once you know the material, it doesn't matter how much the material you have. The density is some value, right? Some ratio of mass to volume. Okay. Here's Archimedes principle all over again. Buoyant force is equal to rho vg, if you like, or rho gv, if you like. You can multiply these together in any order, right? Right. And that looks a lot like this other formula for pressure. Isn't it true if you dive down into a pool, the deeper you go, you can feel more and more and more pressure? Okay. Is the pressure just very simply directly proportional to the depth? Like if you're twice as deep, is that twice the pressure? Yeah, that's exactly what this does. And if you look at these two formulas side by side, they're really similar. Right? They both got the density of the water. They both got the gravity field. Right? But if you want pressure, you just multiply by your depth. If you want the buoyant force that helps push you up, you try to make you float, you got to multiply by the volume that you're displacing. That's it. Right? How about this? If you go deeper, 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 that's more and more and more and more pressure. Right? But what about buoyant force? What if you have an ice cube and you push down the ice cube and you just barely submerge it? So it's right near the surface of the water, but you push it down a little bit. And there's definitely some buoyant force trying to make it bob back up. Okay. Then you push this down like a mile down into the Atlantic Ocean, and you're like a mile down. Okay. Now there's definitely way more pressure, isn't it? Okay. Is that more or less or the same buoyant force? Same. Aha! It's the same buoyant force. It's the same pressure differential. All right. So a little fun observation there. Okay. Here's a classic question that I don't know if it's gonna quite fit in this year, but you might see this. Hey, maybe in college you might see this, right? Is if you have if you have an ice cube or an iceberg that's like way, way, way bigger, do you think the same proportion of that ice is submerged underneath the water? whether it's a little cube or a big old iceberg. Yeah, it turns out. And if you want to solve for that proportion, you can set up an equilibrium. I mean, that's the start of this. It's going to kickstart this whole process. Turns out the answer is just very simply the ratio of the densities, right? Ice compared to water, right? We'll tell you exactly what proportion is submerged, right? And for ice compared to water, it's about 90% is underneath. All right, so that's a fun one. That's good to know. Does this show up? Yeah. All right, it does show up. If you look very carefully on your puzzles right here, I think that actually is a question. That does show up. Yeah, that's right. It does show up. Aha. That's it. All right, YouTube. I think I showed you this the other day. So again, review. Do you guys think the pressure right here and the pressure right here have to be the exact same pressure? Yeah, equal pressure at equal depth for the same liquid. That's actually called Pascal's principle, is that the pressures have to be exact. But where do these pressures come from? Because on the left side and the right side, it's two different stories how you get to the exact same pressure. Okay? So if I follow the left arm of this tube, I got, and you guys know what pressure is. Let me rewind a couple of slides here. It's this expression right here. So density of, well, if it wasn't water, if it was any fluid, this could be any fluid, right? If it was oil or something. The density of the fluid times gravity times however deep it is, right? So I got this rho g h naught here. That's right here. Plus this rho g h1 plus this rho g h2. Now this is a different rho because maybe it's a different fluid, different I don't know, some kind of oil or something, right? Okay. Plus, don't forget, if this is open to the atmosphere, is the atmosphere also pushing down from above? Right? Like a whole atmosphere pressure, right? So I got that all added up over here. Boing, 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 boing. Right? How do we get the same pressure from the right side? Well, I got this rho GH naught here, this right here. I got this rho GH2. I got this rho this rho GH3, ain't that? Right? Got this rho GH4. And also, if this is open to the atmosphere here. Right? Now, there's different variations on this. So sometimes one end is sealed closed, so you don't get the atmosphere. Mine is open at both ends. That's why the atmosphere on both sides. And since mine has the atmosphere pushing down on both sides, can that cancel out there? Okay. And this rho GH naught, what's up? Okay. So just these four terms left there. So these two terms and these two terms have to equate. Okay. All right. So that one's fun. Okay, let's look at, here's a hydraulic lift. I think you guys also got a hydraulic lift. If you're looking at the paper in front of you, it's number 108. That picture looks like that picture. Guess that. So the principle here is that it's the same pressure on this hydraulic fluid. Right? Pressure is transmitted undiminished. Right? And pressure is the ratio of force to area. So if you have a small force acting on a small area piston, that's equivalent to, that can hold up a large weight on a large area piston because it's the same ratio. Is that? Okay. I think I'm going to go back and edit this poster because I wrote equal pressures at equal depths. Now, that's only true if it's the same fluid. So that kind of falls apart. Like right here, that wouldn't be true, right? Because you got different fluids going on, right? And also if the fluid is stagnant, which it is on this picture. But later on today, we're getting closer to, we're about to put fluids into motion. And when fluids are flowing, that's going to be no longer the case. Okay? You guys okay? Okay, good so far. Who's got any questions so far? Right. So far, it's been mostly review, and you guys are going to get to apply some of these principles. Like, can you apply Pascal's principle to this hydraulic lift right here, for example? Right. And find out later today. Okay. Here's some new stuff. You guys ready for some new stuff? New stuff. Right. Let's get this water flowing through a pipe system. You guys see a large pipe leading into a small pipe right there. You guys see that? Right. So this might be some good notes here if you want to keep some notes. Right. I'm going to get that picture going. So let's have a large pipe feeding into a small pipe. Okay. Have a transition right here. Okay. And I'm looking at some, I'll call this a cross-sectional area, maybe a smaller cross-sectional area here. Okay. Okay. So I'll call this A1 and A2. A for cross-sectional area. Okay. For a pipe. Okay. So okay. Now let's have some water flowing through. So there could be maybe some speed of the water. Suppose you watching some debris float by, you put a radar gun on it, it's going to read some speed. I'll call it V1. Okay? V for velocity, right? Like speed. Okay? Now, when the water goes into the small pipe, is it going faster or slower in terms of linear speed? What do you think? Who says faster? Who says faster? Yeah, it is. So I'm going to make a arrow vector that's a little bit longer just to really get the idea across that's going faster. I'll call this V2. Okay. So we got A1, V1, and A2, V2. You guys get it? Okay. Now I'm making the claim. I mean, you guys kind of know where this is going anyway. This gold box here. Supposedly, if I multiply those together, that's conserved, right? But I really want to lead into that so you guys see the full process of how it ends up at that place. Okay. Right. Now I'm really going to back up and give you guys some extra details too, because just like little details that's good to know in life. Pipes are oftentimes named in terms of their diameter. So if let's say you're out in the field one day and somebody says, "Oh, there's a 10-inch pipe buried underneath ground here." 10-inch pipe, guys. If somebody says a 10-inch pipe, they're referring to the what of the pipe? Diameter. Aha. So like this diameter here, right? And I'm gonna label that D for diameter. Okay. Guys, what is diameter compared to radius? Yeah, it'd be twice, right? Right. Like if this was the radius here, the diameter would be twice the radius. Is that true? Right. Now here's where I'm gonna flip this over and do some notes on the back here. It's been working out very well today like this. Right. Let's look at this cross-sectional area of a pipe. Say if water, could you imagine if your fish swimming through the pipe system? It feels like you see you're swimming like into the paper. This is going to be the cross-sectional area of a pipe. Right. And then what do we got on here? Let's call this right here the radius. And if you like, maybe this whole thing could be the diameter. Okay. Right. So I know that radius is diameter over 2. Right. Or if you like, diameter could be twice the radius. Right. So that could be helpful. Right. Now there's a couple formulas that students every year like mix up. But we've talked about this a long time ago in this class. I want to see if you guys get it. Like, what's the circumference of a circle and what's the area of a circle? So let's start with circumference. What's circumference of a circle? 2 pi r. Yeah. And if you like, in terms of diameter, could that just be pi times diameter? Right? Because what's the area of a circle equal to? Ah, pi r squared. All right. Oh, good thing I got a sharp class here. Yeah, pi r squared. Right. Right. Here's the 2 formulas that students mix up all the time every year. It's circumference and area. Right. But if you know how units work, then you'll never miss it. You'll never forget this. Because guys, could that radius be measured in meters? And circumference, that's 1 trip around. That could also be in meters, couldn't it? So those would definitely have to be directly proportional. Right? But area, guys, area is not measured in meters. Area could be measured in what? Meters squared, square meters, right? Is that true? Right? Okay, so whatever the radius is, you'd have to square that first, wouldn't you? Right? Here's what this looks like on a picture. If I take this radius and I square it, and I hatch this in, you guys see this square that I'm hatching in right there? Isn't that the radius squared? Right? Guys, suppose I want to paint this original circle. You guys see this original circle? I want to paint it. And you buy some paint. And how much area do I have to cover? How many of these squares that I hashed in would exactly cover that circle? Huh? Well, it'd be less than 4. Huh? Pi! Yeah, the answer's right here. It's been here the whole time. Whatever that r squared is, that's what I just hashed in. Multiply by 3.14 gives me the circle. Guess that? Right. Now, next question. What is the area of a circle, not in terms of radius, but in terms of this whole diameter right here? Mark that off, call that D for diameter. What is that? What is this area? Okay, let's do a little substitution. In this, actually, yep, sorry, that's backwards. Oops, this is what I meant to do. Let's do it that way, forget this one. Okay. Diameter is twice the radius, right? What did I just do? No, I was right the first time. Oops. All right, I'm all over the place. Sorry about that. Let's do this one. Let's do this one right here. Instead of radius, I'm going to substitute in diameter divided by 2. Is that okay? Okay, that's what I meant to do. So I got pi times, and instead of radius, I can just do d over 2, right? Now it's still being squared. Don't forget that. Right? There's 2 on the bottom. Can you square that? What's 2 squared? 4. And I can pull that out front. Now it's still in the denominator. Could that be pi over 4 times diameter squared? Could that be? You guys get that? Guys good? Okay. I think we may have done that last semester. Maybe like the first or second week of school. Yeah. So again, that's just a little bit extra information. So if somebody tells you like a 10-inch pipe, can you guys take 10 inches, square that, multiply it by pi over 4, you get the area in square inches if you wanted to, right? Maybe you'll see that someday, possibly, right? All right, that was a little extra. All right, so let's go back to this pipe system. And again, I'm trying to get to this conservation of flow. So I want to roof off some volume. I'm going to make a cylinder shape here. You guys see this cylinder? Maybe I'll hash it in and peak, just make it really stand out. You guys see this pink cylinder right here? That's all water. Okay. Now, if I want an equal volume of water over here, then how long does the cylinder have to be? Like if this is X1, should X2 be really long to have the unequal volume of water? Let me hash that in to try to make it pretty close. You guys see, could that volume and that volume be the same volume? Like they're both 1 gallon or both 1 cubic meter? Okay. And I'm going to call this distance right here X2. Oh, it's X2. Okay? That okay? Okay. Now, if all this water is flowing through this pipe system, could it be the same number of gallons per minute everywhere, or the same cubic meters per second in metric? Okay, that's what conservation of flow is. So let's get that on the board. All right, so this cylinder, let's do this. Let's do volume per unit time is equal to volume per unit time everywhere in that system, because that would have to be true, right? Volume per unit time, right? As long as the water is not compressible, which is true. Okay. And what is the volume of the cylinder equal to in terms of its area and x? Is it just this area times x? Is that it? Yeah, so that's what volume is. So the area 1, x1, okay, all in some time because it's flowing, equals, and then over here I got a different area and a different x over time. Is that okay so far? Everything I wrote? Say, okay, that follows, that follows, that follows. Okay. Okay. Now, what is this thing right here? What is distance over time called in physics? Velocity. Aha. So area 1, velocity 1 equals area 2, velocity 2, because this is a velocity 2 over here, isn't it? Right? All right. Ah, look at what we just got. That right there. That's this gold box right here. Is it? So there's conservation of flow. So cross-sectional area for the pipe times however fast the water is flowing through it. That product is the same everywhere in the pipe system. Okay? Is that? Let's go some numbers at this. Okay. Let's say the original cross-sectional area was like, 12 units. I don't know, maybe 12 square meters. And the water's flowing through it, let's say 3 meters per second. Is that okay? Okay. And now over here in the smaller pipe, I'm going to throw in an extra little question right here. Suppose, you guys ready for a bonus question? Suppose the small pipe diameter is half the big size pipe diameter. Could this diameter be about half of this? Okay. Guys, if it's half the diameter, it's how many times the area? And don't say half. 1/4. Yeah, 1/4. Okay. Because that goes back to this relationship right here. If it's half the diameter, half squared is a quarter. Ends up being a quarter. Okay. So, then what number should I write in the set of parentheses then? Aha. Yeah. Oh man. All right. Let's do this. Can I go back and make a change? Is that okay? All right. I want to change the speed of the water. I just don't want 2 3s to show up on my page. I didn't need to do that. Can I change the speed to 5? Is that okay? All right, 5 meters per second. Let's do that. All right, let's do that. All right. So yeah. So I got 3 square meters because half the diameter should be quarter of the area. Like, maybe it's really obvious in terms of squares. Right? Because what if I didn't have a what if I did not have a circular pipe? What if I had a square pipe and it has like half the width? You guys see that the area would be 1/4? And that's way more obvious, right? In fact, does the shape even matter at all? Did it even have to ever be a circle? I don't think we ever dealt with this pipe before even, right? If we're talking about proportions. Because what if I had a pentagon shaped pipe? And it had a pentagon cross-sectional area. Right? Would it still scale the same? Would area still be proportional to the width squared? Yeah. It doesn't matter the shape of the cross-section. It doesn't matter if it's a circle or a square or a pentagon. Right? That does not matter. Right? Right. So here we got to finish this off though. Who can tell me? Because the water was originally going through it. This is supposed to be a 5 meters per second. Who can tell me how fast is the water going now? Ah, 20 meters per second. Oh yeah, 20 meters per second. Right? Because 12 times 5 is 60. 3 times 20 is also 60. Right? Or in terms of proportions, because if you have 1/4 of the area, is that 4 times the speed? Yeah. Right. You guys see that? Right? There's conservation of flow right there. Conservation of flow. Right? You guys good with conservation of flow? Okay. Now, really, all we did was for this gold box for an incompressible fluid. So water has a constant density. It doesn't matter how much pressure, it's always the same density. Right? So water is not compressible. Right? If you did have a compressible fluid, because suppose you have steam going through here. Now, steam could definitely be compressible, right? The extra that you have to consider is the density of the steam. So that's where I threw the little rows right here. Is that right? Because it can be more or less dense, right? I don't think you're going to run that into that in this class, though. But I don't know. Maybe if you're an engineer someday. Right? But in this class, the gold blocks are faithful. Okay. You guys see that? All right. Let's extend the story. I'm going to put a little goldfish in my pipe system. That's this little goldfish swimming around. Okay. Natural environment pipes. That little goldfish swimming right there. Right? All right. So this fish is swimming along, swimming along. Now, you guys know going from the big pipe to the small pipe, the water, slows down or speeds up? Speeds up. Now it's going faster. Right? But from the perspective of the goldfish, I want to ask a question, not about speed, but about pressure. Right? Does this fish feel the same pressure here as here? Yes or no? Turns out no, right? Because turns out moving fluids, the pressure actually changes, right? Now, do you think going from the big pipe where the water's moving slow to the small pipe where the water's going fast, is the pressure on this fish going to increase or decrease? Huh. Let me see a show of hands. What do you guys think? How many of you guys think that the fish feels an increase in pressure? Who thinks that? How many of you think the fish feels a decrease in pressure? Who thinks that? Huh. Right. And you know what? I'm going to do a quick experiment to kind of reveal the answer to you guys. Right. I got this paper, guys. This paper right here. I'm going to prove it to you guys by blowing a stream of air over the top. That would be a moving fluid, wouldn't it? Like right now, the air is not moving. I'm going to make the air move. That would make it move faster. Right. Right. When I do that, either the paper is going to be pushed down, which would indicate a high pressure, or it's going to be vacuumed up, which would indicate a decrease in pressure. What do you guys think is going to happen? Because that would answer that question, wouldn't it? About the fit. Let's see. Let's do some science right here. I blow a stream of air over the top. You guys see the paper getting vacuumed up? You guys just see that? So what you guys just saw is that when a fluid speeds up, what happens to the pressure? It decreases. This fish is going to feel like the pressure just decreased, as if he had swum closer to the surface rather than diving deeper down. Isn't that true? Like the effect would be the same, right? Okay. So you guys just saw a moving fluid decreases the pressure. Huh, right? So what I'm trying to lead into, and I had to start with conservation of flow, but the next step is going to be something called Bernoulli's principle. Hey, look who it is. It's the goldfish. He's right there. He's always going to be there. Right. So, actually, we got even more things going on with this one. Not only is this fish going from a big pipe into a small pipe, like the last time, he's also changing elevation too. Right. Now let's handle those effects one at a time. Right. No. See if you guys just got this. Going from a big pipe to a small pipe. I'm ignoring the delta H. Just going from a big pipe to a small pipe. That by itself does what to the pressure on the fish? Increase or decrease? Decrease. Right? How about this? Even if the water wasn't flowing, just a change in elevation. I'm just focusing on the change in elevation now. Because if you go from the bottom of a pool to the top of a pool, that feels like what happens to the pressure? Also decrease, right? Because I know the deeper you go, the more the pressure, the shallower, the less the pressure. Okay, so I think there's two effects that are both going to decrease the pressure on this fish, right? Right, the faster moving fluid because it's smaller pipe, but also changing in elevation, okay? Okay, and it's all handled by this Bernoulli principle right here, okay? Ooh, guys, take a look at this equation. Now, I want you guys to see where this comes from, but let's look at the end result first, right? How many different terms do you guys see here? 1, 2, 3, 4, 5, 6. Do you guys see 6 different terms? Right? Let's say we're going from maybe this point in the pipe system to this point in the pipe system. Got a bunch of terms added together. And I bet some of you guys are catching on to this might look kind of familiar to something from last semester. Guys, does this look like conservation of energy? Does that almost look like conservation of energy? You guys think? Right? Because guess what? It is in disguise. let's see where this comes from. Let's say conservation of energy. Let's say you have some energy. I don't know. Maybe it's thermal energy. Maybe it's chemical energy. Maybe it's energy in a spring. Right? I'm going to add. If I lift this object and set it on a table surface, what is the what kind of energy did I just give it? Potential energy. And what's the formula for that? mgh. Okay. Right. And let's say it's also in motion, which means it has what kind of energy? Kinetic. What's the formula for that? 1/2 mv squared. Right. And let's say that's all initial conditions. So I threw a bunch of subscripts for initial. Okay. Let's say sometime later in the system, it has a different amount of internal energy or other kind of energy. It changed height. If it changed height, it's got a different mgh. And if it changed speed, it has a different 1/2 mv squared. All right. That looks like a pretty general, comprehensive conservation of energy equation, doesn't it? Okay. Now, if I want to start with that and somehow end up with this box here, right? I mean, these do look really similar, right? Instead of this m, I have, guys, what character is this again? Rho, which stands for what? Density. How do I go from mass to density? What do I have to divide by? Volume, right? Because mass divided by volume gets you to density. Is that true? All right, let's check this out then. So if I divide this term by volume, that would make this match this. But if I divide this term by volume, what do I have to do to these other 5 terms to balance the equation? Also divide by volume. Right? Divide. Is that okay? Right? Let's see if you guys are following. What does this V stand for? Is this volume or velocity? Volume. Aha, volume. Okay. So circle this right here, this right here, this right here, and this right here. Everything I just circled, that does represent density, doesn't it? Okay. Now, back in the energy days, we had like definite discrete masses that were definitely some point masses. Okay. But if you have a continuously moving fluid, maybe it's easier to think in terms of density, isn't it? Right? How about this? Energy per unit volume. I wonder what that could be. What is energy measured in? Joules? Here, I'll do this on the back of the paper. Say energy over volume. What is that? Okay. Well, I know energy is measured in joules. Volume is measured in what? How big is the box? Some number of cubic meters, right? And 1 joule breaks down into, well, newtons times meters, because I know work is force times distance. That would tell me that. I got cubic meters. Newton per square meter. Hey, Newton per square meter. What is that? Huh? There's 1 Newton weight on 1 square meter foam board. Gives you 1 Pascal, which describes the pressure. Pressure. That's what that is. That's pressure. Right? Is that true? Right. Go back here. Right here. Okay. This right here is pressure. And this is pressure. Okay. So put it all together. I got some initial pressure plus rho GH plus 1/2 rho V squared. Right? And then somewhere else in the system, I got a different internal pressure plus rho GH plus 1/2 rho V squared. Okay. But this is final and this is final. Oh, whoops, and this is final. I meant to do final. Yeah, initial, final. Okay, so I still got 6 terms. Is that okay? Okay. And these pressure terms represent the pressure that the fish feels pushing on them from the water, right? Okay. So let's do a quick numerical example. You guys ready to do an example? Okay. Let's say, actually, let's start with something realistic, and then I'll boil it down to something simpler. Okay. How much atmospheric pressure are you sitting in right now? How many pascals? Yeah. 100,000? We're sitting at 100,000 right now? Okay. Now, I'm really going to simplify this just to make the numbers look nicer. Let's say I had like 100 units of pressure. I'm going to call that pascals. Okay. Plus, let's say there was like some height. I'll call that, let's say like 10 units of pressure. I'll say pascals just to tag a unit to it. Let's say the motion of the fluid also came out to like 10 units of pressure that I'll call pascals. Okay. Okay. And let's say I'm solving it for this picture right here, where the fish swims to the skinny pipe that's elevated. You guys got that? Okay. And I want to know what pressure does the fish feel up here? So that's what I'm solving for. Let's solve pressure final right here. Okay, solve for that pressure. Okay. And then, just to kind of make up numbers, just so you guys can see the force for the trees example. Okay. The fact that you're elevating higher, which H is bigger? This H on the right or this H on the left? This one on the right, because you're more elevated. Which means that this pressure term is going to be what? More than or less than the original 10 pascals? Has to be more than. So let's say you run the numbers and it comes out like 20. Okay? Could that be true? Okay. And now let's consider the fact that you're going from a fat pipe into a skinny pipe. Is the water moving faster or slower than before? Faster, which means this 1/2 rho v squared final is what? More than or less than the original 10 units? Has to be what? Yeah, it has to be more than. Right? Again, I'm just going to make up a number. Let's call it 20 units again. Okay? All right? You guys get it? Is that okay so far? All right. Again, you could have specific numbers to the. You could have a specific speed and a specific height, and you could plug those numbers individually in. Right? But who can solve that equation? Who knows? What pressure does the fish feel now? 80. Aha! 80 pascals. 80 pascals. Yeah, it definitely is less, isn't it? It's definitely less pressure than before, right? Because 110, it was 120 originally, and this also adds up to 120. Okay, guess that. Guys, all right? All right. Again, if you had the density of water is 1,000 kilogram per cubic meter, gravity is like 9.8 meters per second squared, and there's some specific height change that was given, and you kind of figure out what the new speed of the water is, you can plug those numbers in individually and sort of solve it that way too. Okay. All right. Oh, yeah. Go ahead. All right. So this is the main things I want you guys to see today. So the title of this video, when I upload it to Google Classroom, I'm going to title it Conservation of Flow and Bernoulli Principle, because those are the main takeaways from today. Okay. Now, you guys saw a bunch of review posters also, and I do have a couple of little bonus posters. Right, so let's do a little bit of bonus here. Let's do some ideal gas law. Okay. Here's some questions that I think I asked before, but every time you see it, every time you hear it, think about it. Easy to remember it. Okay. So this relates the pressure, volume, and temperature of some gas. Let's say a balloon is tied off, for example. N is how much gas is in the balloon. R is just a constant to make the numbers work. Like, are you measuring volume in liters or cubic meters? Because you'll get different textbook values of R just to make the numbers work. Okay. So let's start with the Boyle's law version of this ideal gas law, pressure and volume. Suppose I have this balloon and I squeeze the balloon down. What just happened to the volume of that balloon? It got smaller. Okay. Now, let's say the temperature stays the same, just to keep it simple. Temperature doesn't change. Okay. If the volume is half of what it was before, and there's a fly flying around, what new pressure does the fly feel? It's how many times what it was before? 2 times. Half the volume can be twice the pressure. You guys see that inverse relationship? Right? As long as the temperature is the same. Right? How about this? Let's keep the pressure the same, and let's heat up the balloon, change the temperature. Okay? Because if I heat up the balloon, increase the temperature, what happens to the volume of the balloon? Also increases. Does the balloon expand? Okay. All right. What if you double the temperature? If you double the temperature, the volume changes by a factor of 2. Yeah, so double, right? Could that be? Right. Are you guys ready for the curveball question? If the temperature goes from 10 degrees Celsius to 20 degrees Celsius, is that doubling the temperature? How many guys say it is? How many guys say no? Aha, it is not. Because can you put Celsius into this temperature? No. Because notice it doesn't just say temperature, it says absolute temperature. You can't use Celsius, you have to use what? Kelvin. Aha. Okay. Now going from Celsius to Kelvin, it's a very simple conversion. All you do very simply is add what? 273. 273, that's it. They're scaled the same. A change in 1 degree Celsius is the same thing as a change in 1 Kelvin. So they're scaled the same. They have different specific numerical values. So just very simply add 273. Okay. So when I say you go from 10 degrees Celsius to 20 degrees Celsius, that's really going from 283 Kelvin to 293 Kelvin, which is a tiny proportion change. I think, did we run those numbers the other day? It was like a 3.5% change. I think it was. Yeah, something like that. I'll do it right here. So 10 to 20 degrees Celsius, that's really 293 Kelvin from 283 Kelvin. If I divide that, that's a change of about 3.5% right there. Okay. Right. So then the volume of the balloon would be expanding, but only by about 3.5%. So it's a little bit bigger. All right. So we got that. All right. On the puzzles I gave you guys today, there are a couple of expansion questions. So let's just hit that real fast. This is pretty straightforward. Because most materials, if you heat them up, don't they usually expand? Right. Now, how much? Well, the change in length is equal to the original length times the change in temperature times, and this alpha is something called coefficient of thermal expansion. So I gave you guys some numerical values for that. Okay. On number 93, there's a bridge that's heating up from January to August, so it heats up. And this superscript didn't print very well. So I'm giving you the thermal expansion of steel is, it says 12 times 10 to the negative 6, and the unit is 1/kelvins. Okay? All right. Okay. Which is also, if the next question talks about a block of concrete, it turns out that the coefficient of thermal expansion is exactly the same. It's actually, we'll say it's the same number. Okay. That has an interesting consequence, but I might talk about that more in the future. Now, the bridge is pretty straightforward. This is the answer to the bridge question. Right? That's the whole thing. Right? The concrete block, can you guys possibly think about this in 3 dimensions, like length, width, and height? Right. So the next one's a little challenge question there, but I want to see how many students get that right. Okay. All right, let's take a look at this page I gave you guys. So I could walk you guys through step by step how to solve exactly every one of these, but I'm going to try this a little bit different this week. So I want to see if you guys, either by yourselves or in teams, can apply everything that I taught you guys over the last few days to these more challenge type questions. Some of these are a little bit more straightforward. Some of these are a little bit more challenge. All right, but let's look at these real fast. So the first 2 questions have to do with this piston. Ooh, guys, piston. Do you think these first 2 questions have to do with the ideal gas law? Right. Now, one of these, you're changing the temperature. And the next one, well, you're putting a weight on it, which is like changing the pressure. And pressure is force per unit area. That's the weight divided by this area. That'll get you kickstarted on those. 2 different questions. I got a statue, some weight in the air, some weight in the water. Ooh, this one sounds like the Archimedes principle demo that Paul Hewitt did. Right? You're trying to figure out what's the density of the material. Again, there's a little bit of complexity here. There's a little bit of a puzzle challenge. See if you guys can solve that. Right? But it starts with Archimedes' principle. Apparent weight of a rock submerged in water. Suppose there was a scale at the bottom of a pool, and you drop the rock on that scale. How much does it show on the scale? Density of salt water, density of ice. What percentage of an iceberg will float in the water? Ooh, that is exactly answered by one of the posters that I showed you earlier today. Ooh, figure that out. Okay, we got the bridge expanding and the due to temperature change. I just showed you guys that one. Now the block of concrete, you have to think in 3 dimensions because it's like a block. So you can figure that out. Ooh, hydraulic lift. Is that Pascal's principle right there? Hydraulic lift. And the last 2 questions here have water flowing through a pipe system. There's a conservation of flow and a Bernoulli principle question. Boom, boom. You guys think you can solve this? All right. On the other side are 4 more challenge questions. So I got a boat full of iron. You guys see a boat full of scrap iron. Now, guys, does this boat push down into the water equal to its own weight? And the water pushes up with what kind of force? What kind of force is holding the boat up? Buoyant force. I gave you guys a free body diagram right here. Guys, look at this nice free body diagram. That'll kickstart this problem. That'll really help you guys out. Here's the question. When all the iron is in the boat, the water is at some level on the side of the pool. Then we're going to take all that iron, we're going to dump it overboard. It's going to sink down to the bottom. This water level is going to change. What's the change in the water level? Ooh, so there's all the little parts that you have to get right for this. Let me help you guys out with this right now. When the iron is in the boat, it pushes down into the water. It displaces an amount of water equal to the what? Equal to the volume of iron or equal to the weight of the iron? Or I don't know if I phrased that exactly correctly, but the here, this free body diagram helps you out. The iron pushes down equal to its own weight, and the amount of water displaced has to equal that weight. So the weight of water displaced matches the weight of the iron. Okay. Right. When the iron is dumped overboard into the water, it displaces an amount of water equal to its own what? Equal to its now I got the iron sitting down here at the bottom of the pool, equal to its own volume. Aha. Right. Right. Now just to help you guys visualize this a little bit. Okay. If I have this tank right here and I start filling this with water, fill this with water, and I want it to match the weight of this weight that I'm holding right here, so they're equal weights, right? Equal weight water to what I'm holding in my canter, right? Which would be more voluminous, the weight itself or the water? I think the water would be more volume, wouldn't it? Okay. Okay. So you guys have to think kind of deeply on that, but I want to see who can figure that one out. Next one. I got a submarine. It's floating here, and then eventually crashes down to the bottom of the ocean. Yeah, what's the buoyant force? Right, question. Right. Look at the scale here. So we have the scale. It's all balanced here, but when you dunk this weight in, it tips the scale. Now that one's a deep thinking question. I want to see if you can figure that out. Right. And they got two objects, a cube and a sphere, that have the same surface area. And what's the ratio of the buoyant forces? Right. So got some deep thinking questions on that side. Right. So you guys have the rest of today and all of tomorrow to work on these teams, and I'll see you guys where you guys are at the end of tomorrow on these puzzles.